Brothers and sisters, it's Dr. Brizendine here, and I wanted to reach out to you on our Lab 4. So part of what I do with some of our assignments is I try to find things that can prevent cheating, can prevent people from going and trying to find answers that may or may not be out there. And that's part of what I did with this. I evaluated a number of different possible binaries for us to attack, and I thought this would be a good one that we could use, that we could do the NX always on and force and necessitate ROP as the mechanism by which we would bypass DEP. Whereas previously, this did not need DEP. And as you could see from our last video, it looked very, very promising. I did some initial testing, and I thought, this is a good, challenging binary. Not too hard, not too difficult. We have the issue with Virtual Protect not being there. So that gives a little bit of a challenge. Are we going to find a way to use Virtual Protect, which you could do if you could get ROP to work? Or alternatively, you can do the more challenging Virtual Alloc. So it looked really good. Problem is, though, as I was evaluating this, I did not fully evaluate it, and I did miss one key critical step, and so unfortunately, as far as I can tell, I really don't see any way for this to be plausible for ROP to work on this. So what we're going to do is we're going to explore why that's the case, give you some insights into that, and then we'll introduce the revised version of Lab 4. So in a sense, we'll kind of dumb it down, but it still will be something of a challenge. I think we'll all learn something from Lab 4, even in spite of these challenges here. So let's go ahead and take a look and see what we got cooking and what the problem is here. So I've gone through, I got default Mona for Virtual Alloc. We set that up, we're ready to go, and we can go down here. We see it's going to create an exploit. We have some junk, and then the ROP chain. I'm not showing you the part of the junk. That's for you to figure out. But if we did it just right, and we did, it would go right here. So if I wanted to check on this, I would want to set a breakpoint right there, which we will do in a second here. Let's get this cleared out. So let's go and open this up, and then we will attach it. I guess not that. We want to get our breakpoint. We can check and see that it's ready, and we are ready to go. And so now, all that is left for us is simply to at the breakpoint, we have the exploit that we created, and we see that we got it. We have the pop-pop-ret right there, and from there we can, well, at this point I want to focus in on our ESP. So this is part of the problem here. So some of you, one person noticed it. I got an email from John Streff and Brian Furman yesterday informing me of this. So we can investigate this. We have some A's here, some other junk variables. And then we see this address, and that corresponds to right here. And if we go to the next one, we see right here that it's not what we have there. So we're missing all of this. And why are we missing that? The little thing here I missed out on is the null byte. So the null byte effectively truncates everything after that point. And so my initial thought was, we really are screwed, right? How can we do ROP if it truncates that? And then my next thought was, well, are we really screwed? Is it possible that it could persist somewhere else in memory? Very, very high chance that it probably is somewhere else in memory. But is it somewhere that is reachable? That's the question. And so I thought I would answer that question. One good way to do that is to search for a pattern. If I look at what I have here, I really don't have a very good pattern. So that doesn't work out too well. Just for sake of ease, I could make it so that we do have a really good pattern. So I might do something like plus Bramwell, that's my name, and place that there. And see if that ends up anywhere in memory. There are other ways where we could search with exactly what we have, but the way I'm going to show you is perhaps just a little bit quicker and easier. So that's why we're doing it this way. So let's go ahead and reopen that and attach it. We want to get that initial breakpoint, which is this. Okay, so we are ready to resume and then launch it. Launch our attack. And I think I have. Oh, I can't tab that. Okay, so let's drop that in there. And we got it. So now I want to search for my name because it's such a wonderful name. So PyMona, and then find. And again, all this information is the PyMona manual. You can Google it, mona.py manual. And you get the documentation there. So type, and then ASCII, and then string, and then Bramwell. So it'll search through the totality of process memory for that tag. And it looks like we found it. It's on the heap. Well, isn't that special? And one thing, and so I was thinking, is there a way I can reach the heap? So and we can also just view it over here. And so Bramwell starts there. And then beyond that we have all this other stuff. The A's, which is the initial point there where everything begins. And so the question is there a way we could pivot? We'll get one gadget, one ROP gadget that would maybe work. Can we pivot there? And so I was thinking, is there a way we could do that? And then I noticed that, maybe there is a way, because if we look closely here, we want to consider the different addresses. So as I'm looking here, trying to figure out the possibility, let's see, EBX. So let's look at EBX. So EBX is actually the start of our payload. And if we go down here, we see that it has everything. So then my thought was, well, okay, it's an EBX. Can I get to EBX with my one single solitary gadget? You know what? Let's find out. So we are limited to a certain number of modules. ASLR is what stops us. If it's true, we can't use it because we don't have an ASLR bypass. But right here I see ASLR false. So we only have one, which is coolplayer.exe, the image, the process image itself, right here. So we can use anything in there, but anything else we cannot absolutely use. And so there is a way we can check and find that. There are certain so if we do the traditional Mona, PyMona ROP, we'll find, assortment of different ROP gadgets and other goodies, but we don't find things like jump to dereferenced pointer of a register. And that's really what I want here. What I want is, well, we'll see it in a second here. So the command I would use is find wild, and then we do the string there, and then we can enter what it is we're looking for. So I could do jump dword pointer EBX dereferenced. So that means we go to EBX, and then whatever address is contained it EBX, which I've messed this up here, so let's change it here. It'll go to this location, it'll dereference that, and then it'll go there. Right now there's nothing at 41414141, but if it were an address, it would go there and execute that. So this could be a ROP gadget, this could be a ROP gadget, this could be a ROP gadget. So that was my thinking. And then we wanted to confine it to a certain module, so we do the -m and then the coolplayer.exe. And let's see what, if anything, we get. We do get some stuff. That's awesome. So we could do that. We could dereference that. And so we could take this and we could place it, well, maybe not there, but we can just ignore everything else here at this point. Whenever you give me any kind of anything like this, make sure that it's always annotated. I may not accept it if it's not, just because I'm not going to take the time to look up every little thing like this. That's ridiculous. So make sure that your things are commented appropriately. So I have that there. I could save that and go there, but what that would mean is instead of starting on the stack, it would start right here. So that's an idea. Is it necessarily a good idea? Well, it's debatable. Is it the solution? No. Because we would run into the same problem as before. Only, we would have, because it would truncate, we would not overwrite EIP on the stack. So if we had addresses here, like these addresses right there. So what am I saying here? So instead of having a junk, we would take the ROP chain and move that to where the junk is, so that the addresses are right there, and we would use these addresses to cause the overflow, and then we could then jump over there with our jump dword pointer EBX. So it's an interesting idea, but the problem is, again, the same thing, the null byte. It would truncate it. So we would never have the opportunity to overwrite EIP, because instead of using the junks, we would have this. We would have, and by this I mean these addresses. So the end result then is that, unfortunately, we wouldn't overcome EIP, and the fact that it's over an EBX would not help us. We wouldn't get that far. So it's a good idea, and it's an interesting exploration. But that still doesn't necessarily resolve what we're trying to do with our Lab 4, which obviously we have to change it, and we are going to change it. So let's talk about that aspect of it now. So I had you do BCD edit set NX always on. Now we're going to change it back to opt-in, the traditional. So we completed that. So let's go ahead and exit out of everything here, and we can go ahead and restart. So this is something you want to do, because we want to remove the always on and return things back to the way that it was. So with our new assignment, what we're going to do is we're not going to have to overcome DEP. We're just simply going to get the shellcode and go directly to the shellcode. So let's look at that and see what that looks like here. So instead of having ROP gadgets, we won't use ROP gadgets. What we will do instead is we'll need to find, perhaps the best way to really explore this is to get it going and take a look and then see. So this one right here is what we would use to overwrite EIP. Okay, so let's see what we get here. Let's get this open and drop our exploit into it. And we had the jump dword pointer dereference EBX is our breakpoint. This is what we capture EIP. We do it with this. So that works. But in terms of what we're trying to do here, that doesn't help us, because now we've changed it. We made it NX opt-in instead of NX always on. So that means, because this is a very, very old application, it's not compiled with the NX compat protection, meaning there's not dep for this, for the coolplayer.exe. So if we can get something on the stack or on the heap, then we can execute it as instructions. But this gadget's not going to do it for us, because it'll go and jump and dereference it. We want to have jump. If we had jump EBX, that would work. So that would mean that we would have EBX, we would have our instructions, our shellcode right here, and this would interpret it as shellcode. The other place we could look at is ESP. So let's go see what we got over at ESP. So let me change this here, see exactly where it is. So ESP. So yeah, this should work for ESP. So we could do a jump ESP there. And again, we can check our modules. We need to make sure that there is no ASLR. The only one that has no ASLR is this false right here, so CoolPlayer. So when we do our search, we limit ourselves to that. Let's try our jump ESP and limit it to that. Really? Okay, 0 pointers. Sorry, it's not going to work. What about EBX? Can we do a jump to EBX? And then that would execute it as instructions so that we could have shellcode. So when we're trying to bypass DEP, we encounter addresses. So like our jump dword pointer EBX, we would encounter addresses and we could do it that way. But if we can do jump EBX and if DEP is not in place, we just execute that straight shellcode. So that's what we want. So can we find that? Nope, it does not exist. So does that mean game over? Well, not quite. There is another way. But I'm not going to tell you because we still need to have a Lab 4, right? And we don't want to make it too easy. So what you're trying to do for Lab 4 here, or revised Lab 4, is to capture EIP. Then we need to find a gadget to get us either to EBX or to ESP, and then we can run these as instructions rather than shellcode. So what do I mean by that? Well, so right here, this is an address. It's an address on the stack at ESP. If I do U, then that means it's going to go there and execute these as instructions. Or I could do the same with EBX. I could go there and execute those as instructions. Increment EAX. But I would need some gadget to get us there, some gadget to enable us to stack pivot. So the word stack pivot is kind of a clue. So as you're trying to figure out how to pivot to that, you might do some research. Do some research on stack pivoting. We're limited simply to one gadget. We get one chance. The initial thing that we use to capture EIP with. That's our one gadget. And we have to get either to EBX or to ESP. And then once we accomplish that with our one gadget that you need to figure out, then we need to have appropriate shellcode instructions. And I don't care what you use for shellcode. It's perfectly up to you. The only thing is, it should really be benign. If it's malicious, then again, indicate that to me. And you also need to be aware of no bytes. So that's a bad character. So if you're doing EBX and you put a no byte there as part of your shellcode, then you'll never get your initial EIP overwrite. So keep that in mind with bad characters. And it's possible there could be other bad characters. You could investigate that if you wanted. So this week has certainly been interesting with the coronavirus and everything else. And I didn't anticipate this issue with Lab 4, but I think it makes for an interesting challenge. I'll look for another lab for us to work on ROP with. And so once we get our ROP out of the way, we're going to start talking about shellcode and egg hunters, which an egg hunter is a type of shellcode. You'll be writing custom shellcode yourself. with assembly instructions. So that is on the horizon for us. So I'll close out this video and wish you guys a good weekend and good luck on your lab.